Hello everyone. In this lecture I am going to discuss about leaf springs from mechanical springs from the course DMM1. So now see what is a leaf spring. These leaf springs are like flat plates which are placed one over the other, which may be of different dimensions. Okay, and by using a U-bolt or any band, they are attached to the here at the center. They are attached here at the center, and the other eye end of this leaf spring is attached to the body of the vehicle with the help of here this is a shackle pin or shackle. Leaf springs also known as, let's see the definition. Leaf springs also known as flat springs are made out of flat plates. These are flat plates. The advantage of the leaf spring over helical spring is that the ends of the spring may be guided along a definite path as it deflects to act as a structural member in addition to energy absorbing device. See, these are placed in a guided pattern, and apart from taking these absorbing the shock loads and these vertical or lateral loads, it will also act as a structural member. When it comes to its flat position after the application of load, it will act as a structural member like our beams, simply supported beam, cantilever beam. Okay. Thus, the leaf springs may carry lateral loads, brake torque, driving torque, etc., in addition to shocks. These loads and torques will also be taken by these leaf springs, in addition to shocks. So let's see the derivative part of this leaf spring. Consider a single plate fixed at one end and loaded at other end. Okay, fixed at one end and is loaded at the other end. This is like our cantilever beam. This is a flat spring cantilever type. Let T is the thickness of the plate, T is the thickness of the plate, and B is the width of the plate, and L is the length of the plate at which the W is acting from the fixed part, from the fixed cantilever end. We know that maximum bending moment. In cantilever beam, we know that bending moment will be at this point, which is A, and the maximum bending moment is load into distance. Okay, here the bending moment is maximum, W into L, M is equal to W into L. Okay, and section modulus, we know that M by I is equal to sigma by Y. So we need to calculate sigma in that relation. Before that, we are calculating Z, section modulus, which is I by Y. I is moment of inertia, and Y is the distance from the neutral axis, okay, to the outermost fiber, which is I BT cube by 12, moment of inertia, and Y is T by 2, okay, which will be BT square by 6. Next, bending stress. We know that M by I is equal to sigma by Y. By using that relation, we are finding out sigma. Stress is equal to M by Z. Okay, since I by Y is equal to Z, sigma is equal to M by Z. And M we have already known, W into L, and Z, BT square by 6. WL by BT square by 6 is equal to 6WL by BT square. This is the equation 1. We know that the maximum deflection for cantilever beam with concentrated load at the free end is given by, we know the deflection formula for cantilever beam, which is WL cube by 3A. If we substitute these values here, the I value and W value, then we will get 4WL cube by EBT cube. If you write this relation in terms of sigma or stress, you will get 2 by 3 sigma L square by ET. 2 by 3 sigma L square by ET. This is deflection. Next, see the stress distribution in this cross section. This is the thickness T, and the stress bending stress diagram will be like this, because if load is acted here, the topmost fibers will be in tension. Okay, it will deform like this. The topmost fibers will be in tension. Okay, and the bottommost fibers will be in compression. Bottom fibers will be in compression, top fibers will be in tension. Okay, if it deforms like this. So here that topmost fibers, it is showing that they are in tension. Okay, and the bottommost fibers are in compression. Next, see, the shear stress distribution will be like this. If you calculate the shear stress across this cross section, the shear stress distribution will be like this, and at the center the shear stress is maximum. Okay, the maximum shear stress will be at the center. This is shear stress distribution. If the spring is not of cantilever type but it is like a simply supported beam with length 2L and load 2W in the center. So now see the flat spring with a simply supported beam type. Okay, if you join two cantilever type of beams, you will get this simply supported beams. We generally use this type of configuration in vehicles, automobiles. Okay, so we are taking that simply supported beam with length 2L, L1 is equal to 2L, and load 2W at center. Okay, maximum bending moment. Here the bending moment maximum will be at the center. Okay, and if you calculate the bending moment, you will get, if you calculate from right side, you will get W into L at the center. Okay, that is the maximum bending moment. M is equal to W into L, and section modulus Z is equal to, this is also the same cross section, B into T, rectangular cross section, BT square by 6, which is I by Y, BT cube by 12 by T by 2, which will be BT square by 6, because the similar cross section like the previous cantilever type. Next, bending stress sigma is equal to M by Z. You know M by I is equal to sigma by Y. From that relation we got sigma is equal to M by Z, which is WL by Vt square, which is similar to 6WL by Vt square. We know that maximum bending moment of a simply supported beam loaded in the center is given by simply supported beam maximum deflection equation is delta is equal to WL cube by 48 EA. WL cube by 48 EA. But here the W1 is 2W and W1 is 2W and L1 is equal to 2L we are taking. So substituting those values here, you will get WL cube by 3EA. Okay. From the above, we see that a spring such as automobile springs, generally we use semi-elliptical springs, leaf springs, with length 2L and loaded at the center by load 2W may be treated as a double cantilever beam. This is how we will treat this as a double cantilever beam. If the plate, because these are similar, if the plate of cantilever is cut into series of N strips of width B and these are placed as shown in the figure, see if you cut the previous, we have previously taken a cantilever beam, right? That cantilever beam with B as width and T as thickness, right? We have to cut it into 3 strips. Okay, each strip will with thickness T. Okay, if you see this configuration, the equations for these will be in the denominator you have to add n. Okay, because n number of there are n number of plates are there. So in the denominator you need to add n. This will give you the stress and bending stress and deflection equation for this configuration. Okay, simply you need to add n in the denominator for both these equations. The above relations give the stress and deflection of a leaf spring of uniform cross section. The stress at such a spring is maximum at the support. The stress is maximum at the support. If a triangular plate is used, if this type of cross section is used, the stress will be uniform throughout. The stress distribution will not be changing. Okay, the stress distribution will be uniform throughout. If this triangular plate is cut into strips of uniform width and placed one below the other as shown in figure 2.23.29b, this one, to form a graduated or laminated leaf springs. So if you cut this triangular plate and place it like this, this is the top plate or full length plate, it is called full length plate, and the bottom plates, which are also called as graduated plates, are placed like this. Okay, this dotted pink lines are showing these graduated plates. Okay, the total one will look like this, the full length one. For this configuration, the stress is also 6WL by NBT square, and delta is equal to 6WL cube by NEBT cube, which is equal to sigma L square by ET. Okay, these are also same equations. A little consideration will show that by the above arrangement the spring becomes compact, so the little space occupied by the spring is considerably reduced. By using this type of configuration, the stress distribution will be uniform throughout, and also the space will be reduced. The space required for this placement will be reduced. Okay, then see, when bending stress alone is considered, the graduated leaves may have zero width at the loaded end. Okay, if you only consider the bending stress, and if you do not consider the shear stresses, then this the width at this point will become 0. Okay, so for that condition we should not take zero width at this point. Okay, so because there are shear stresses also acting at that point, but sufficient metal must be provided to support the shear. This is the point. Therefore it becomes necessary to have one or more leaves of uniform cross section extending clear to the end. So you need to place two of these full length plates here. Okay, for compensating that. We see from equations 4 and 6 that the same deflection, the stress in uniform cross section leaves, full length leaves, is 50% greater than in graduated leaves. The stresses generally here, if you see, the stresses will be maximum at this full length leaf, which was the top one, and compared with the graduated leaves. Okay, if you see these relations, assuming that each spring element deflects according to its own elastic curve, with the suffixes F and G are used to indicate the full length and the graduated leaves. Then now see this relation, you got this full length and graduated leaves. See this relation, delta is equal to 2 by 3 sigma L square by ET. Okay, let's consider this sigma L square by ET as x. This will be 2 by 3 x. Now see here, this way for this graduated leaves, sigma L square by ET. Okay, therefore those full length plates, 2 by 3 deflection is 2 by 3 x. Okay, and here it is only X. This X is for graduated plates. Okay, graduated plates, and this 2 by 3 X is for the full length plates. Okay, and if you write this, if you take this relation, then you can find out the deflection. This is the deflection equations, right? 2 by 3x for full length plates and only x for graduated plates. From these relations you can know that sigma f is equal to 3 by 2 sigma z. From that relation you can find sigma f is equal to 3 by 2 sigma z from that relation. Okay, and if you substitute these values of sigma f and sigma g, 6wfl by nf bt square is equal to 3 by 2 6wg l by ng bt square. You cancel out all the similar terms, 6l 6l, bt square, then this will be the remaining part. Wf by nf is equal to 3 by 2 into wg by ng. Okay, adding 1 on both sides, you will get wf plus wg by wg is equal to 3nf plus 2ng by 2ng. Okay, therefore wg is equal to, if you take this wg this side and take this side, then you will get wg is equal to 2ng by 3nf plus 2ng. Okay, into wf plus wg. This wf plus wg will be taken as w because it is a total load on the spring which was carried by graduated leaves and full length leaves. Okay, and here wg is the load taken up by the graduated leaves, and wf is the load taken up by the full length leaves. From equation 7 we may write wg by wf is equal to, similarly here we write wf by wg. If you write wg by wf is equal to 2 by 3 ng by nf. If you find out all those similarly, we get wf is equal to 3nf by 2ng plus 3nf into capital W. Okay, if you substitute this wf equation in this sigma f, we know that sigma f is equal to 6wfl by nf bt square. Okay, bending stress of full length leaves is equal to, if you substitute this wf value here, then you will get 18wl by bt square into 2ng plus 3nf. This is the equation you are going to use in the problems. Okay, you need to remember this equation, and you know that sigma f is equal to 3 by 2 sigma z. And similarly we find for the sigma g is equal to 2 by 3 times of sigma f. This 18wl by bt square into 2ng plus 3nf into 2 by 3. Okay, then you will get 12wl by bt square into 2ng plus 3nf. Okay, then we use this equation in design problems of leaf springs. And also this is deflection equation. The deflection in full length and graduated leaves is given by delta is equal to 2 sigma f into L square by 3 ET. Then you substitute sigma f value, this one here, you will get 12wl cube by EBT cube into 2ng plus 3nf. These two equations you need to know because you will use these two equations in formula in design problems. Okay. Next, construction of leaf spring. This is how the leaf spring will look like. There are generally two types of configuration. Here it is shown that U-bolt type of configuration, semi-elliptical leaf spring, and there is also a band type of configuration where a band is used to place these all leaves at one place. Okay, and here while placing one leaf over the other, the shapes are also important. These square and tapered, egg shaped end and ordinary rounded end, these shapes are required to place or to join one leaf with the other effectively. Okay, if you join these effectively, if you want to join these effectively, you need to shape these ends like this. Okay, like shaped ends, square and tapered, ordinary rounded end. Okay, and if you use a band here, then this overall length L, small l is there, right? That will be ineffective. Okay, that will not participate in taking up those shock loads or any lateral loads or torques. Okay, then from the effective length 2L1, this should be removed if you use a band here. Okay, if you use a band here, here if you at this place, if you use a band here, then this place, if you use a band here, then this overall length small l will be removed. Okay, from the effective length while calculating, while doing the design. And if you use like this U clamp and central bolt like this, then only one L by 3 part is removed. Okay, from this effective length for the operation. Okay, and this rebound clips are used to join all the leaves. Okay, place the leaves at a place. Okay, this top one is called the main leaf, and the bottom one, which is same in length of the top leaf, these two are the full length leaves, and the remaining bottom leaves are the graduated leaves, which are having different shaped ends. Okay, this type of configuration is called semi-elliptical leaf springs. These are generally used in automobiles. Now see, equalized stress in spring leaves, which is also called nipping. We have already discussed that the stress in the full length leaves is 50% greater than the stress in the graduated leaves. In order to utilize the material to the best advantage, all the leaves should be equally stressed. See, we know that the top full length leaf is 50% more stressed than the graduated leaf. Okay, so for the equalized design, we need to equate both the stresses. Okay, the stresses in both the plates should be taken as same stress. Okay, this condition may be obtained in the following two ways. These are two ways: by making the full length leaves of smaller thickness than the graduated leaves. The thickness of this full length leaf should be reduced. Okay, full length leaves is reduced, then the stress will be equal. Sorry. In this way, the full length leaves will induce smaller bending stress due to small distance from the neutral axis to the edge of the leaves. If we take the cross section, if you see, this is the cross section of this full length leaf. Okay, if you cut here, this is the cross section of the full length leaf. The neutral axis will be here, the distance will be this one. If you decrease the thickness T, let's think this is T thickness. If you decrease the thickness T, then it will look like something like this. The width is same. If you decrease the thickness, then it will look like this. Then the distance will be reduced, distance from the neutral axis. So it will become equally stressed with the graduated leaf. Okay. And there is another, by giving a greater radius of curvature to the full length leaves. This radius of curvature, if this radius is greater, curvature is greater to the graduated leaves, then it will also compensate that before the leaves are assembled to form the spring. This radius of curvature is more before joining by using U bolts or any band. The curvature is more, then it will also compensate this stresses equal. It will also make the stresses equal. By doing so, a gap or clearance will be left between the leaves. see this left gap which is called C, which is called nip. Okay, and if you join these two by using any U-bolt or any band, then the initial stresses will be developed. Those are called initial stresses if you join these two to form a leaf spring. Now see, consider that under maximum load conditions the stress in all leaves is equal. Then at maximum load the total deflection of the graduated leaves will exceed the deflection of full length leaves by an amount equal to the initial gap C. Okay, generally the deflection of graduated leaves is equal to deflection of the full length leaves plus this gap. Okay, because at initially they are used to join these two with the help of initial stresses. These two are joined by using a bolt or any band. Okay, so these stresses are developed. From that relation you get delta G is equal to delta F plus C. From this, C is equal to delta G minus delta F. If you substitute this equation, it will look like this. Since the stresses are equal, therefore sigma G is equal to sigma F. We must design for the equal stresses in both graduated leaves and full length leaves. So sigma G is equal to sigma F. 6WG into L by NG BT square is equal to 6WF by NF BT square. From this relation, if you cancel out all the similar terms, you will get Wg by Ng is equal to Wf by Nf, which is also equal to W by N. Okay, these are similar, right? This ratio is similar. Just take it as that it will be is equal to W by N. Now write Wg is equal to, take this Ng that side, Ng into Nf into Wf, which will be equal to Ng by N into W. Okay, Wf by Nf is equal to, we know, W by N, some relation. And similarly Wf is equal to Nf by Ng into Wg, and this Wg by Ng is equal to Nf by N into W. Okay, we are finding now Wf by taking this Nf that side. Wg, it will be in terms of Wg by Ng, Wg by Ng into Nf. So Nf by N into W. Okay, it will be equal to some W by N ratio, right? Substituting the values of this Wg and Wf in this relation, then we will get 2WL cube by N into EBT cube. Okay, 2WL cube by N into EBT cube. Now the load on the clip bolts required to close the gap is determined by the fact that the gap is equal to the initial deflections of the full length and graduated leaves. And there is also another fact that the gap is also equal to, the C gap is also equal to the deflection of both these leaves. Okay, full length leaf and graduated leaves. Sorry. C is equal to delta F plus delta G. Substitute these values. C we have already found out here, 2WL cube by NEBT cube. That will be equals to delta F deflection of full length leaf 4L cube by NF EBT cube into WB by 2 plus 6L cube by NG EBT cube into WB by 2. Okay, these are the delta F and delta G relations. From this, if you cancel out all the similar terms, then you will get W by N is equal to WB by NF plus 3 by 2 WB by NG. Okay, if you take this 2 NG NF common, then you will get this relation. WB is equal to 2 NF NGW by N into 2 NG plus 3 NF. And the final stress relation will be, the final stress in spring leaves will be the stress in the full length leaves due to applied load minus the initial stress. Okay, uh, for calculating the stress, final stress, you need to remove the initial stress from the applied load. Okay, stress in the full length leaf due to applied load. And sigma is equal to 6wf by nf square minus 6l nf square into wb by 2. This value was due to this initial stress. See, these two are joined, right? wb by 2 into this l, that will be here. Okay, 6l, if you take out this 6l by nf square common, you will get wf minus wb by 2 into, and if you solve this relation by substituting these values wf and wb, you will get 6wl by nbt square. Okay, and this n is also equal to nf plus ng, which is where n is the number of leaves and nf is the number of full length leaves plus ng is the number of graduated leaves. The final stresses in the leaves is also equal to the stress in graduated leaves due to applied load plus the initial stresses. So generally they are designing for the same. The final stresses will be equal in both these graduated leaves also. The deflection in the spring due to the applied load is same as without initial stress, and the deflection is also same for the applied load without the initial stresses. Next, see the length of the leaves. I have already discussed this. If a band is used in this place, then the effective length 2L is equal to 2L1 minus L. Okay, if a band is used in this place for a length small l. Okay, if this type of configuration is used, like U clamps or U bolts, then you can take 2L1 minus 2 by 3L. Okay, 2L1 minus 2 by 3L. Now let's see the design problem on this. Design a leaf spring for the following specification: total load 140 kN and number of springs supporting the load 4. We are using 4 leaf springs here. Like if you take a vehicle, it will have 4 wheels, right? On each wheel you place 1 leaf spring. Maximum number of leaves 10. Span of the spring is 1000 mm. The length is 1000 mm. Here you need to take 2L is equal to 1000. Okay, permissible deflection is equal to 80 mm. Delta is equal to 80 mm. Take Young's modulus E is equal to 200 kN per mm square, and allowable stress in spring material as 600 MPa or 600 N per mm square. Let's see the given data. Total load 140 kN, number of springs 4, and number of leaves n small n is equal to 10, and length 2L is equal to 1000 mm, or then L is equal to 500 mm, and delta 80 mm. E is equal to 200 kN per mm square, which is 200 into 10 cube Newton per mm square, and sigma is equal to 600 MPa, which is 600 Newton per mm square. And we know that load on each spring, the total load is 2W, which is equal to total load by number of springs. This total load was given, right, 140 kilonewtons. That was taken up by the 4 leaf springs. Okay, so 140 by 4, which will be 35 kilonewton. This is 2W is equal to 35. Now W is equal to 35 by 2, which is 17,500 newtons. Okay, now for this design you need to find out the thickness and width of the leaves. Okay, we know that bending stress sigma is equal to 6WL by NBT square. You substitute all the known values here, and we are not substituting in here, you can substitute also. Then we will get NBT square is equal to 52.5 into 10 power 6 by 600, which is 87.5 into 10 cube. Let's take this as equation 1. You can also substitute n value here, we also know 10. Okay, then we will get BT square equation. Okay, but here we are taking NBT square equation. And we also know that deflection delta is equal to 6WL cube by NEBT cube. Okay, in this relation also we'll substitute all the values, and you will get nbt cube is equal to 65.6 into 10 power 6 by 80, which is equal to 0.82 into 10 power 6. If you divide this to 2 by 1, you will get t is equal to nbt cube by nbt square is equal to 0.82 into 10 power 6 by 87.5 into 10 power 3. If you solve this, you will cancel out all the terms, and you will get t is equal to 9.37, which is approximately 10 mm. And if you substitute this 10 mm in any of these one equation, t as 10, you will get 10 square here, and n we already know number of leaves 10. Then you can find out the b value 87.5 mm. Okay. .5 mm. And you can also calculate this value using this relation number 2 equation. Okay, then you will get, you have got 82 mm here. So generally in design problems you need to take the maximum value. You have to take the maximum value of these two, which is 87.5, which is approximately 90 mm. Okay, so the 90 mm is the answer. Here the design is based on this bending equation. Let's see another problem. A truck spring has 12 number of leaves, 2 of which are full length leaves. There are 2 full length leaves in this n is equal to 12 number of leaves. The spring supports are 1.05 meters apart, and central band is 85 mm wide. Here we are using central band, okay, not U-bolts. The central load is to be 5.4 kilonewtons. The total load 2W will be 5.4 kilonewton. Okay, with a permissible stress of 280 megapascal or 280 newton per mm square. Sigma is equal to 280 newton per mm square bending stress. Determine the thickness and width of the steel spring leaves. It's the design problem, so you need to find out the thickness and width, T and B. The ratio of the total depth to the width of the spring is 3, and the ratio is also given depth to width. Here the total depth will be n into T. There are number of leaves, right? You need to add all those thicknesses. Okay, n into T. That is the total depth, and width is the same B. Also determine the deflection of the spring. You should also find the deflection of the spring. See the given data. Number of leaves n is equal to 12. Number of full length leaves is 2 given. 2L1 is equal to 1.05 meters. It is also given 1050 mm. And small l is equal to 85 mm. Length of the band given. 2W is equal to 5.4 kilonewtons, 5400 newtons, which from this W is equal to 2700 newtons. This is 2W given 5.4. So W is 2.7 kilonewtons or 2700 newtons. And sigma F is given 280 megapascal. Okay, this permissible stress is for full length leaf. Sigma F is equal to 280 megapascal or 280 newton per mm square. Thickness and width of the spring leaves. T is equal to thickness of the leaf and B is width of the leaf. These two you need to find out. And it is also given that relation, since it is given that ratio of depth, total depth of the spring, which is n into T, total depth. Generally depth will be T. Here there are n number of leaves, right? There are 12 leaves, so n will be 12 into T. Okay, and width of the spring is B. N into T by B is 3. From this relation we will get 4T, which B is equal to 4T. Okay, since n is equal to 12. We also know that for a band type of leaf spring, 2L is equal to 2L1 minus L. Okay, for a band type of leaf spring. Then 1050 minus 85, which is equal to 965 mm. Okay, and L, this is 2L value, and L is equal to 965 by 2, which is 482.5 mm. Number of graduated leaves. Only full length leaves are given. Now we are finding out the number of graduated leaves. Ng is equal to 12 minus 2, which is 10. Okay, since there are 2 graduated leaves, total number of leaves 12. The remaining 10 leaves are the graduated leaves. Assuming that the leaves are not initially stressed, therefore maximum stress or bending. We generally use the full length leaves equation for bending stress equation for finding out this thickness and B. Okay, 280 is equal to 180 WL by BT square into 2NG plus 3NF. Okay, if you substitute all the known values, W is 2700, length 482.5, and B and T, we need to find out T. We are writing B in terms of T, which we have found out here. B is equal to 40 plus T, 40 into T square into 2 into 10 plus 3 into 2. And G we have found out 10 leaves. Now we will get this equation in terms of T cube. T cube is equal to, we got 805.3, then T is equal to 9.3, which is approximately 10 mm. Now B is equal to 40, 4 into 10, which is 40 mm. Okay, here we find out thickness and width of the plates or leaves. Now we have to find the deflection. You know that deflection delta is equal to 12 WL cube by EBT cube into 2NG plus 3NF. Okay, if you substitute all the values, W 2700, L 482.5, E 210 into 10 cube, we are assuming that E is equal to 10 into 10 cube, and B 40, and T 10 cube, T cube 10 cube, 2 into 10 plus 3 into 2. Then we will get 16.7 mm. This is how you will find out the design. You will do the design of a leaf spring. Thank you. For reference purpose, you can use RS Gourmet textbook. Okay. Thank you.